Welcome to Lesson 4D, What Happens Downstream of a Converging-Diverging Nozzle. In this lesson, we'll discuss the flow downstream of the exit plane of a converging-diverging nozzle. In other words, what happens to the jet down here when the back pressure is lower than that required for a shock at the exit plane. I'll introduce such terms as ideal expansion, overexpansion, and underexpansion, and we'll discuss why rockets have multiple stages. First, a review from the previous lesson. We have our converging-diverging nozzle with all these different conditions, and we plotted both pressure and Mach number as functions of x, the distance down the duct or nozzle. And recall that PE should be up here, since this is a very strong shock at the exit plane. I won't go through all these cases in detail since we did that in the previous lesson. We're going to concentrate on what happens downstream of this converging-diverging nozzle. When back pressure is greater than PC, which is this case, we get a subsonic jet at the exit plane, since the flow is subsonic. When back pressure is less than PC, but greater than PE, which is another way of saying case D, any case D in here, for any pressure like that in this range, you get a shock somewhere in the diverging portion of the duct. In the case where PB is PE, has the shock right at the exit plane. For any of these cases, we still get a subsonic jet, since flow downstream of the shock is subsonic. And as we discussed last time, when PB equal PF, we have ideal expansion, and the jet that comes out the exit is supersonic, but nice and straight. The jet looks something like this, eventually becoming subsonic, of course, as it expands and slows down. I want to concentrate now on the case when PB is greater than PF, but less than PE, in between these 2 points on our pressure plot. What happens in that situation? Well, let's think about it. PB is greater than PB for ideal expansion, but PB is less than the PB required for a shock at the exit plane. That's case E. But we know that for any PB less than PE, the flow is choked or frozen in the entire CD nozzle. There are no shocks in the nozzle, so we approximate the flow as isentropic. Now let's discuss what happens downstream of the duct. The pressure here is PE with lowercase e meaning exit. Don't confuse that with case E, which is an uppercase. And PB is the actual back pressure of the gas outside this duct. And for the case we're talking about, PB is greater than PE. Since PE equal PF, the ideally expanded case, since everything in here is frozen or choked, even though PB is greater than PF, PE will be equal to PF. Well, then what happens to the jet? Well, the jet has to get pushed in, since the pressure out here is larger than the pressure here. Well, the jet coming out here is supersonic, but converging, so the Mach number starts decreasing, just as if we had a converging duct again. Well, this leads to all kinds of expansion and compression waves and other complications and some shocks. In fact, I'll show more detail about this later, but we get something called shock diamonds. They look pretty much like diamonds like I sketched here, and there's all kind of expansion and compression waves within each of these. And people call these shock diamonds because of their shape, and other people, especially pilots, like to call this flow a tiger tail because it has stripes like a tiger tail. This case is called overexpanded. It's an overexpanded nozzle or an overexpanded jet. Of course, these shock diamonds will become weaker as we go downstream, and all these cases eventually become a subsonic jet. Another way of explaining overexpanded is that the increase in area in the diverging part of the duct is too large for the back pressure. We've overexpanded the duct. If PB were small enough, namely PF, it would be ideally expanded, but it's too big for that, so the flow has to adjust itself. Now consider the case where PB is less than PF, which we called case G. This is the opposite case to the overexpanded jet. In this case, PE is still equal to PF, but PB is less than PF, therefore less than PE. So the pressure right here is greater than the pressure just outside the jet. So the jet must flare out, the opposite of the overexpanded case. In this case, the jet is pushing the outer gas outward. We call this underexpanded. It's an underexpanded jet, and this condition is called flare out. Again, the Mach number here is supersonic, and the flow has to turn something like that. This is similar to the underexpanded nozzle that we discussed in a previous lesson. As PB continues to decrease, the flare out is more severe. Let's sketch 3 cases. First, case F, where the jet is ideally expanded. And then I'll look at 2 different cases for case G, namely slightly underexpanded. That's the case where PB is slightly less than PF. And we'll consider a second case G. I'll call this G1 and G2, where PB is very small and we get a huge flare out. I'll call this highly underexpanded. PB is much less than PF. PB can actually be a total vacuum, which is what we find in outer space, so any rocket nozzle will have severe flare out. Here's a practical application, namely rocket design. At launch, PB is P atmosphere at roughly sea level, and the rocket is typically designed to be slightly overexpanded, which is the situation where the jet gets turned inward. Since the flow is going like this at an angle, we don't have maximum thrust efficiency. This is a compromise because as the rocket goes up to some altitude, PB is now the local atmospheric pressure, which is of course less than P atmosphere at sea level, since pressure decreases as we go up in altitude. And at this particular altitude, we have ideal expansion instead of overexpansion. This would be the case F, where the jet comes out nice and straight, and we have maximum thrust and maximum efficiency. But as we keep going up, and the rocket goes up even higher, PB gets smaller and smaller, and now we have underexpansion. Now the jet flares out like that.
I would think that with such large flare out, the thrust would decrease because the exhaust gases are coming out at an angle rather than straight down. Yeah?
Good observation, Albert. The jet's now coming out like this, and so we don't get efficient thrust. In fact, at even higher altitude, we have a highly underexpanded jet, and the rocket exhaust is coming out at angles nowhere near straight down. We get very poor efficiency and low thrust. So what do? We ditch this rocket stage and start a second stage. The second stage rocket will be designed for a very low atmospheric pressure, and rocket scientists have to figure out how much to overexpand the jet at liftoff, where the maximum thrust should be, and how high they want to go until they have to get rid of this stage and start up the second stage. Here's an example of an actual rocket engine. This is a first stage rocket engine, which is what you would use at liftoff. The exit to throat area is 16:1, and for all these rocket problems, we'll use gamma of 1.33, which is pretty typical for rocket exhaust. The throat is around here, and the exit plane is 16 times bigger area than the throat. We want to calculate the Mach number at the exit plane. Well, this problem is very simple. We know that A over A star is 16 as given, so we solve this equation for M, noting that it is an implicit equation as we've discussed previously, and there are various ways you can do this. Using any method you want, we'll let ME be M at the exit plane. I get 4.13 to 3 significant digits. Now consider a second stage rocket engine. I do the reverse problem here. I give you a higher Mach number at the exit, 5.0, and we need to calculate the exit to throat area ratio. Again, we use gamma as 1.33, and we make our typical assumptions and approximations. You can tell by looking at this that the area ratio is going to be a lot larger, with the throat here and the exit here. In this case, we can solve explicitly at m equal 5 and gamma equal 1.33, so the exit area turns out to be 37.4. Compared to the first stage, this is huge, more than double, since AE over A star was 16 for the first stage. When you get into outer space, where you have satellites, the back pressure is nearly zero. In other words, near a total vacuum. So the area ratio, AE over A star, is huge, as you can see here. This would be our A star, and this would be our AE. Here's a couple other cases with an even bigger area ratio for satellite thruster rockets. These can be as high as 150. Note that Mach number doesn't go up very much as area keeps getting bigger and bigger. For example, at an area ratio of 150, we can calculate the exit Mach number. It turns out to be about 6.6, which is big, but to get closer to ideal expansion, you'd have to keep making this area bigger, and you get diminishing returns. And don't forget that in real life, there's friction along these walls. I'll end by showing you lots of pictures. Here are shock diamonds, and you can see that they rapidly dissipate, with the flow eventually becoming subsonic. This is an overexpanded nozzle, as we discussed. Notice how the jet angles inward, and you see some shock waves here. This is an attempt to explain what's going on here, with expansion waves and compression waves and some shocks, etc. Here's a cool picture of the SR-71 Blackbird with about 7 or 8 shock diamonds that are visible in this picture. Here's a nice picture of an overexpanded jet. Again, the pressure outside is too large for the expansion that occurs in the nozzle, so the whole jet is pushed inward like this. Here's another cool picture of shock diamonds, and yet another. I'll do a quick example problem, since the SR-71 Blackbird was an awesome aircraft. In the literature, you can find out that it travels at Mach 3.2 at an altitude of 24 kilometers, which is about 80,000 feet. Let's calculate its airspeed. To save time, I did the calculations here. We look up in the standard atmospheric table where we have a very low temperature, 217 K. And for air, we can calculate the speed of sound, square root of gamma RT. I get 295 meters per second. And at Mach 3.2, this is almost 1,000 meters per second, or more than 2,000 miles per hour. Here's another picture of beautiful shock diamonds. Now I'll show some pictures of underexpanded nozzles. As back pressure keeps decreasing, you can see that the flare-out gets more and more intense. Here's a picture of a rocket at high altitude for this stage, and you get severe flare-out. Again, this is an underexpanded nozzle. The back pressure here is too low for the nozzle design. And if this rocket has a second stage, this first stage would have to be ejected and the second stage started soon after this picture was taken. Here's some CFD calculations of an underexpanded jet. And then they imitated Schlieren imaging to make it appear like an experiment. Here's an actual experiment of an underexpanded jet. And I won't go into the details. There are expansion waves and compression waves and shock disks like we had previously for the underexpanded nozzle. The next time you watch a rocket taking off or blasting off, look for overexpanded and underexpanded jets and watch for severe flare-out right before there's a new stage ignited. And I think you'll understand more clearly what's going on. Thank you for watching this video. Please subscribe to my YouTube channel for more videos. 1, 2, 3. That's all there is to it.